A nebula is a strikingly bright area of the interstellar medium which may contain neutral, neutrally ionized, or molecular hydrogen in addition to cosmic dust. As evidenced by the pillars of creation in the Eagle Nebula, stars frequently develop in nebulae. These material formations clump together to create denser regions that eventually draw in more matter and reach a density where stars can develop. The leftover material is then thought to form into planets and other objects of the planetary system. Numerous nebulae have diameters of hundreds of light years, which is the size of most of them. A nebula that is visible to the human eye from Earth would appear bigger but no brighter when it is close by. The Orion Nebula, the brightest nebula in the sky that can be viewed unaided and has a diameter twice as large as the full moon, was unknown to early astronomers. Despite being denser than the space around them, most nebulae are significantly less dense than any vacuum that has ever formed on Earth. An Earth-sized nebular cloud would have a total mass of only a few kilograms. The air we breathe has a density of roughly 1,019 molecules per cubic centimeter, but the densest nebulae can have densities of 10,000 molecules per cubic centimeter. Other nebulae are visible because of fluorescence produced by embedded blazing stars, while some nebulae are so diffused that they can only be viewed with lengthy exposures and sophisticated filters. There are some nebulae with varying T-Tauri star luminosity. Initially, nebula was the term used to describe any scattered astronomical object, including galaxies outside the Milky Way. Spiral galaxies in general and the Andromeda Galaxy specifically were referred to as spiral nebulae prior to Vesto Slipher, Edwin Hubble, and others establishing the true nature of galaxies in the early 20th century. As Edwin Hubble discovered, the bulk of nebulae are bound to stars and illuminated by starlight. In order to categorize nebulae according to the type of light spectrum they emitted, he also provided assistance. In 1864, William Huggins started examining the spectra of over 70 nebulae. He found that around a third of them showed signs of gas emission. Due to their continuous spectra, the remaining ones were thought to be composed of a large number of stars. A third category was introduced after Vesto Slipher showed that the spectra of the nebula surrounding the star Merope matched those of the Pleiades open cluster. The nebula consequently radiates light from reflected stars. Slipher and Edwin Hubble continued to collect the spectra from numerous nebulae and found 33 with continuous stellar light spectra and 29 with emission spectra. Nearly all nebulae are connected to stars and are lit by starlight, according to Hubble's 1922 claim. In addition, he discovered that emission spectrum nebulae are typically associated with stars with spectral classifications of B or higher, including all main sequence stars of the O-type, whereas nebulae with continuous spectra are associated with stars with lower temperatures. The nebulae orbiting the hotter stars are transformed in some way, according to Hubble and Henry Norris Russell. There are numerous different formation mechanisms for the various nebulae types. Others are made from gas that is already existing in the interstellar medium, while some nebulae are formed by stars. Examples of the earlier situation include giant molecular clouds, the coldest, densest phase of interstellar gas, which can form through cooling and condensation of more diffuse gas. The material that a star ejected during the final stages of its stellar evolution gave rise to planetary nebulae, which are examples of the latter condition. Huge molecular clouds are associated with star-forming areas, a type of emission nebula. Stars are produced when a molecular cloud collapses under the weight of itself. Massive stars that erupt from the core may ionize the surrounding gas and emit ultraviolet radiation, which causes the gas to become visible at optical wavelengths. The photodissociation area refers to the shells of neutral hydrogen surrounding the H2 region, whereas the H2 region refers to the area of ionized hydrogen surrounding the massive stars. Examples of star-forming nebulae include the Omega Nebula, Rosette Nebula, and Orion Nebula. The nebula may be destroyed a few million years after star formation by stellar winds, ultraviolet radiation from huge stars, supernova explosions of large stars, or outflows from low-mass stars that destabilize the cloud. Supernova explosions, which are the latter phases of the lifetimes of massive, short-lived stars, produce other nebulae. The materials that were expelled during the explosion are then ionized by the energy and compact object produced by the supernova's center. One of the best examples of this is the Crab Nebula in the constellation Taurus. In the year 1054, a supernova event known as SN 1054 was recorded. The compact object created by the explosion has a neutron star at its heart, and it is located in the Crab Nebula. Most nebulae are what are referred to be diffuse nebulae, which are wide-ranging and lack distinct limits. The three types of diffuse nebulae are emission nebulae, reflection nebulae, and dark nebulae. Emission nebulae, also called H2 regions, which create spectral line radiation from excited or ionized gas, mostly ionized hydrogen, and reflection nebulae, which are visible primarily due to the light they reflect, are the two forms of nebulae that emit. Asymptotic giant branch stars are known to lose their outer layers due to strong stellar winds, producing gaseous shells while leaving the star's core behind in the form of a white dwarf. Expelled gases are excited by the hot white dwarf's radiation, resulting in emission nebulae with spectra that resemble those of emission nebulae observed in star formation zones. Planetary nebulae are denser and more compact than nebulae found in star formation areas, despite the fact that they are H2 regions because the majority of the hydrogen in them has been ionized. They got their name because the earliest astronomers who encountered them couldn't tell them apart at first from planets and tended to confuse them with planets, which were more significant to them. It is estimated that 12 billion years after the Sun's creation, a planetary nebula will emerge. Between the late asymptotic giant branch (LAGB) phase and the planetary nebula (PN) phase, a star undergoes a brief period of rapid stellar evolution known as a protoplanetary nebula (PPN). During the AGB phase, the star loses mass and emits a disk of hydrogen gas around itself. At the end of this phase, the star enters the PPN phase. The PPN is energized by the core star, which causes it to produce potent infrared radiation and transform into a reflection nebula. Collimated stellar winds from the central star, which also produce a quickly moving molecular wind, shock the shell into an axially symmetric form. The precise temperature at which a PPN changes into a planetary nebula is determined on the central star's temperature, PN. The PPN phase lasts until the core star reaches a temperature of 30,000 K, at which point it becomes hot enough to ionize the surrounding gas. A supernova occurs when a high-mass star reaches the end of its existence. Nuclear fusion at the star's core is halted, causing the star to collapse. The star erupts as the gas moving inward either bounces back or spreads outward from the core due to extreme heating. The expansion of the gas shell produces a strange diffuse nebula known as a supernova remnant. Although the optical and X-ray emission from supernova remnants is mostly caused by ionized gas, a sizable component of the radio emission is a type of non-thermal radiation known as synchrotron emission. This emission is created by fast electrons oscillating in magnetic fields.